In this video we're going to look at a thermal property of substances called specific heat capacity. We're going to learn what the definition is, how to describe an experiment to find the specific heat capacity of an object, including the measurements you'd take and the calculations you'd make, and you should be able to calculate the thermal equilibrium temperature when two substances are mixed together. Now just imagine that you're on a beautiful beach in the Bahamas. You step out of your hut onto the sand and all of a sudden your feet are absolutely burning. Your only response is to run into the water and dive straight in. But as you're standing in the water, you realise that the water itself is absolutely freezing. Now the water and the beach has been getting the same energy input Q, but the temperature change of the sand compared to the temperature change of the water is very marked. Temperature change of the sand much greater than the temperature change of the water. Now the reason for that, and the things that govern any temperature change, is because they may have had different masses. We know the energy supplied to them was equal, but the energy supplied to an object does help define what its temperature rise will be, and also the material it's made from. Every material will have a different thermal temperature relationship. We can see this if you compare oil and water. If you have oil and water over two heating elements, starting both out at the same initial temperature, if you were then to put the same energy into the oil as you did into the water for the same amount of time, you would find that the oil has a temperature change double that of the water. Now that's the same input energy put into both of them, and it's the same mass of oil and water. So there's something fundamentally different about the materials that make them up. Another interesting thing to show is if this time, starting with the same masses of oil and water, again both at 20 degrees C, this time we put half the energy into the oil that we put into the water, we now get the same final temperature. Or rather, delta T oil is equal to delta T water. But that's with putting half of the energy into the oil that we put into the water. So looking at these two substances, I can see that I have to put more energy into each kilogram of water to get the same temperature rise that I get out of the oil. We can see that this is in fact true because if we look at this experiment that was done by MDR Science, here we have 100 grams of water and 100 grams of oil, both being heated over the same heating element and both starting at the same initial temperature. The water's on the left, the oil's on the right, and as the video speeds up we will see that the temperature of the oil increases much more rapidly than the temperature of the water. In fact, when we get to the end of the experiment, the oil's temperature is double that of the water, even though they've had the same energy put in. The conclusion that we have to draw from this is that there's fundamentally a difference in the way that both materials, the oil and the water, will absorb energy and convert that into a change in the kinetic energy, or the temperature, of its molecules. And this helps us define the specific heat capacity of a substance. We denote it with a little c, be careful it's not the speed of light. And the wordy definition that you need to learn is that the specific heat capacity of a substance is the energy, Q, that you need to put in to raise the temperature of a unit mass, or 1 kilogram, of the substance by 1 Kelvin, which is the same as 1 degree C, without changing the state of the object. So basically it's a measure of how much energy you need to put into a substance to change its temperature by 1 degree C. The unit is joules per kilogram per Kelvin, because we're dealing with energy going in per kilogram per degree of temperature rise, And if we have a look at this little picture down here, you can see a list of different specific heat capacities. Here's water at the bottom with a massively high specific heat capacity. I have to put in 4,186 joules to raise the temperature of 1 kilogram of water by 1 Kelvin. Whereas something like mercury, for example, I only have to put 140 joules in to raise 1 kilogram of mercury by 1 degree in temperature. The bigger the C, the smaller a temperature rise you will get for a set amount of energy put in. We can see this if we look at the way that a balloon responds to a candle. An empty balloon will pop, it heats up very quickly, and that bursts the balloon. But as soon as you fill the bottom of the balloon with some water, water having such a high specific heat capacity will be absorbing the thermal energy from the candle flame. But because it has such a high specific heat capacity, that absorbed energy is going to correlate to a very tiny increase in temperature. And so I can leave the balloon over the candle and it doesn't pop. So here's the equation that links it all together. My change in energy, or the energy that I put in, is equal to the mass of the object in kilograms times the specific heat capacity, which will usually be given to you, although you might be asked to be finding it, times the change in temperature, and that can either be in Kelvin or in degrees C. So let's have a quick practice at using these. Let's bring up our specific heat capacity table again. First question here says, what energy is required to raise the temperature of 2 kilograms of aluminium by 20 Kelvin? Well, I know that my mass is 2. My change in temperature, delta T, is 20. And if I look in my table here, my C for aluminium is 900. If I pop all of this together into my Q equals mc delta T equation, I end up getting, by plugging my numbers in, that I need 36,000 joules of energy to raise the temperature of 2 kilograms of aluminium by 20 Kelvin or 20 degrees C. Now the second question, I'm actually changing that to 7 minutes because the answer that you get for 20 minutes is a bit ridiculous. So, a 3 kilogram block of brass, now we know that brass has a specific heat capacity of 380, is heated by 100 watt, so the power is 100 watts, heating element for 7 minutes. How do I get the energy from that? Well, energy is power times time. My time is 7 minutes times 60 seconds, because I always work in seconds, which gives me 420 seconds. And I know before that my mass is 3 kilograms. We're trying to find out what the delta T is, so if I get Q equals mc delta T, I can rearrange that to get delta T is equal to Q over mc. When I plug in my numbers, I know that Q is equal to 100 times 420, and I know that my M is 3 and my C is 380. When you tap that out on your calculator, we get a temperature rise of 36.8 degrees C, or degrees Kelvin. The final one here says, after heating a 2 kilogram block, so M is 2 kilograms, of silver, so find silver on here and put our C is 230, the temperature rise delta T was 32.9 degrees C. Sorry, its final temperature is 32.9 degrees C. We know that the Q is 5,000 joules. Because we're given that, we don't have to worry about the 10 minutes there. So we've got MC, final time, and Q. First thing I need to do is work out what the change in temperature is. So Q is MC delta T, therefore delta T is equal to Q over MC. Plug in my numbers. And I get a change in temperature of 10.87 degrees C. Now if my final temperature was 32.9 and my change in temperature is that, then my initial temperature in degrees C is just 32.9 minus 10.87, which gives us a change in temperature, an initial temperature in degrees C of 22.0 degrees C. To convert that into Kelvin, I need to add my 273.15, which gives us an answer in Kelvin of 295.15 Kelvin as my initial starting temperature. So that's some basic examples. Now I did say that you needed to know about the experiment to find the specific heat capacity of a material. And basically this is the setup that we have. You have your block here of your material, so that has got a specific heat capacity C that we are looking for. You have a heater that sits in a hole inside that block along with some insulation. Now we're assuming that there is very little delta Q, or transfer of energy, into the insulation. We have our thermometer, and that heating element is connected up in such a way as to resemble the circuit diagram that we see on the right here. Now that means that I'm going to have a current from the ammeter, and I'm going to get a voltage from a voltmeter, so I can get a power for the heater, P equals IV. How did this setup help us calculate the specific heat capacity then? Well, we know that the specific heat capacity equation here is delta Q is MC delta T. So what are we going to need to measure? We're going to need to measure the mass of the block. If we're going to be getting a delta T, we need to measure the starting temperature. We need to measure the voltage, and we need to measure the current. How do we calculate it? Well, the energy in to the block is going to be equal to the power, P is IV, times the time over which it's running. So we're also going to have to measure the time that we're heating the object up for. Once I have a Q, an energy in from Q is IVT, I can substitute that into delta Q in my equation. I know what the mass is because I measured it beforehand. I know what the change in temperature is because I measured the initial and now the final temperatures. So I can rearrange that equation to get Q, or IVT, over the mass times the change in temperature gives us the specific heat capacity. Okay, so let's look at an example of how exactly we would then calculate the specific heat capacity of a material. Now we're told that a 12 volt power supply is being used to heat a 1 kilogram block of copper for 8 minutes. We have a starting temperature, we have a finishing temperature, and we have a current that's read in the circuit. So we know that V is 12, we know that I is 0.68, we know that M is 1, we know that T is 8 times 60, which equals 480 seconds. We know that delta T is 32.3 minus 22.3, which conveniently enough gives us 10 degrees C, and we need to find what the specific heat capacity is. Well, we know that Q is mc delta T. So if I want to get just C on its own, I'm going to get that C is equal to Q over m delta T. Now my Q in this case here is my IVT, which is equal to my 0.68 times my 12 times my 480 seconds. And then if I substitute m on the bottom here for 1 times my delta T of 10, I can plug my numbers into my equation and I get that the C for this particular material is 391.68 joules per kilogram per Kelvin. And it's as simple as that. If we're investigating liquids, we do it in exactly the same way. The only thing that we have to consider for the liquid is the liquid has to be contained within a calorimeter. And the liquid will almost certainly transfer some of that energy into the calorimeter, leading to an increase in the temperature of the calorimeter. But we'd always be given the information needed to put it into this form. Q, or IVT, is equal to the sum of mc delta T for the liquid and mc delta T of the calorimeter. Everything else is exactly the same. So the last thing to do is to have a look at what happens when we mix two objects of different temperatures together. Now here I'm pouring tea into a cup. Thermal energy will transfer from the hotter tea into the colder cup, causing the temperature of the tea to go down and the temperature of the cup to increase until eventually they're going to reach thermal equilibrium. Now let's see what we've got. We have 0.3 kilograms of hot tea at a temperature of 90 degrees C is being poured into a cup with mass 0.2 kilograms and has a temperature of 20 degrees C. It wants to know what will the temperature be when it reaches thermal equilibrium with the cup, and then, and I'm underlining this so I don't forget to go back to it, it asks what assumptions we've made. Well, we're given the specific heat capacities for both the tea and the cup. We know that the mass of the tea is 0.3. We know that the initial temperature of the tea is 90. We know that the mass of the cup here is 0.2, and we know the initial temperature is 20. So if we look at our Q is equal to mc delta T, we need to get a change in temperature. Well, for the T, its temperature is going to go down. So that delta T is going to be 90 minus the equilibrium temperature, TF. For the specific heat capacity equation on this side, we know that the temperature of the cup is going to go up as it absorbs thermal energy from the tea. So we know that delta T is going to be equal to T final minus 20, its initial temperature. So now we can set up a nice little equation. We can say that mass of the tea times the heat capacity of the tea times 90 minus T final is equal to the mass of the cup times the heat capacity of the cup times T final minus 20. So I can plug my numbers into that. I get that 0.3 times 4100 90 minus TF is equal to 0.2 times 720 brackets TF minus 20. If I expand everything out, so if I multiply these two together, times that by the 90 and times it by the TF, and I do the same on this side, I end up with it boiling down to 110,700 minus 1230 TF on this side is equal to 144 TF on this side minus 2880. Now if I collect like terms, so I take this minus TF to this side becomes plus TF, I take the minus 2880 to this side becomes plus 2880, I end up getting that 113,580 is equal to 1,374 times the final temperature. So if I divide that by that, I get that my final temperature TF is equal to 82.7 degrees C. What assumption am I making? Well, the big assumption I'm making here is that no thermal energy is transferring to any other area, or there's no thermal transfer to the air. And that's it. That's how we calculate what the final temperature is when you mix two materials of different specific heat capacities together at different temperatures. That is pretty much all of specific heat capacity. I hope it's been useful.